In this video, we're going to take a look at discrete random variables. Last time we explored the likelihood of events using probabilities, and this time we're going to use these probabilities to create models for making predictions. And most of this is going to rely on those skills that we picked up in creating trees. So our first example, Jessica is playing the video game Pokemon Sun. She knows there is a 10% chance per encounter of finding a rare creature in a given region, and Jessica's going to continue to have encounters until she either finds a rare creature or has 4 encounters. And so let's draw the tree diagram for this scenario. So remember, when we're drawing the trees, we're going to create branching segments that are going to represent each of the outcomes in a sequence of events, or when we're wanting to try and represent conditional probabilities that are harder to put into a contingency table. So for our first encounter, right, we could either get a rare creature, so rare creature, or a not rare creature. And I'm going to use our complement notation, so not rare, to be this case. And there was a 10% chance of getting a rare encounter. So I want to put that in decimal form when I'm using my trees, because I'll be doing multiplication and other operations with it. And then I go on to my next encounter. So now if I got a rare encounter, I'm going to stop, because that's all that she wants, is to get a rare encounter. So the end of the branching is going to happen on R. And then for the not rare encounter, I'm going to try for another encounter. And that could either come out as a rare one or not rare. And then on my next one, I will stop if I had a rare encounter. Otherwise, I'm going to try again. There's rare and not rare. And then I'll do one last time, because I can go up to 4 encounters. And so far I've had 3. And so on my 4th encounter, rare and not rare. Sorry, those complements should be in there. All right, and so now I can add the probabilities to the rest of the branches. Now, we don't know explicitly whether this is independent or dependent. It's not been stated in the problem, but again, when we're given percentage information and not a total to work from, we don't really have a choice. We have to assume that there's independence in each of her encounters. Okay, and that is typically the case with your video game scenarios and other things like that. So that means the probability will remain the same for getting a rare or a not rare encounter. So that'll stay as 0.1, 0.9, 0.1, and 0.9. And remembering those branch segments off of a single node should add up to 1 in each of those cases. All right, so now we can look at the probabilities for each of these, because we're looking at the next question. We're going to let X be the number of encounters, and we're going to want to come up with the probabilities for each of those. All right, and so on the one hand, we have just the straight probability for each of these branches. So I know that the probability of encountering a rare or having a rare encounter is going to be 0.1. And I know off of this branching, I would have a probability of not rare and then a rare. That would be the product of 0.9 times 0.1. And then if I have this other branching, this is going to be the probability of not rare and not rare, and then getting a rare outcome. And that's going to be the probability. Well, I'm having 2 not rare encounters, so I can start to streamline this a bit and notice that that's going to be 0.9 squared times 0.1. And then here I'm going to have the probability of not rare and, oops, let's get those ands in there. And that one. And not rare, and not rare, and last but not least, a rare encounter. And that is going to now have 3 not rare encounters. So I'll take that 0.9 to the 3rd. And then in the last case, I have a rare encounter. And then this final case, probability of all not rare. So not rare and not rare and not rare and one more not rare. It's hiding in there. And that's just going to be the 0.9 to the 4th. So there's our different possibilities, but we want to then think of these outcomes in terms of the number of encounters that we're having. Okay, so the number of encounters, well, in this branching, X is going to be equal to 1, because we're only having 1 encounter because the first one was rare. We're all done. In this next branching, x is equal to 2, since we had 2 encounters, one not rare, one rare. This one, x is going to be equal to 3, and so on, so that this one is going to be x equals to 4 encounters, and this is also a case where we had 4 encounters, right? One of those cases of 4 encounters, we do get the rare encounter in our last case, and in the other situation, we do not. All right, so that's a way. Now, what we want to keep in mind, though, is we can actually use this same outcome tree to look at different variables in this case, right? So the number of encounters was one thing we could be looking at, but we could look at the number of rare encounters, right? So we could say let y equal number of rare encounters. Okay, and so in this case, y is equal to 1 on that branch, y is equal to 1 on this branch, y is equal to 1 on this branch, right? And so on. This would be y is equal to 1 and y is equal to 0, right? And I could look at it in terms of not rare encounters. I could do a bunch of different things that I'm going to look at specifically within a more general scenario. So that's kind of the power of the tree for looking at any of these probability scenarios, is that we can give a picture of what's happening in terms of the actual real life outcomes and then analyze them in terms of different characteristics to create these distributions. So in letting x equal the number of encounters, we can then create a probability distribution. Okay, and that again is a table of all possible outcomes and the probabilities for each of those outcomes. And looking at our tree, we know in terms of the number of encounters, we go from 1 through 4. So we're going to let x be equal to those possible outcomes. So we could be 1, 2, 3, or 4. And now we need to calculate the probability that x is equal to one of these particular values. And that's what that symbolism means. That uppercase X is what we refer to as the random variable. And then we're going to let that equal each of those possibilities. Now, the thing with the random variable X is that there are different likelihoods that it'll be those different values, right? It's not equally likely. And that's where we're going to need to look at these tables and then do different types of calculations, because it's not like data sets or algebra where we would have an expected equal distribution between those individual values. Here we have different weights on them. All right, so let's find the probability of having exactly one encounter. And so in that case, it's only the one branching where x was equal to 1. And so we know that's going to be 0.1. Nice and easy. Where did we have 2 encounters? Well, that was only one of the branches. And that was when we had the 0.9 times 0.1. And that is equal to 0.09. And again, as much as you think you know how to operate, do those multiplications with decimals, use your calculator, have it handy just to verify. It can be really easy to lose track of where that decimal position is going to be. And we're doing calculations where often we're doing 2, 3, 4, 5, 6 decimals out before we're getting our significant digits. So just be aware of that. All right, and then for 3 encounters, that's only happening in the case where we have 2 rare or not rare followed by a rare encounter. And that product should be 0.081. And then we are having 4 encounters in 2 different ways. And that was when we had the 0.9. We had 3 not rare, and then we did get a rare. But then we also want to add to that the possibility of just not getting any rare encounters. And so that would be all not rare, which was the 0.9 to the 4th power. Okay, and those two added together should give us 0.7290. Now, being a probability distribution, so showing all possible outcomes and all probabilities, these probabilities need to sum to 1. So probabilities sum to 1, and we must have included all possible outcomes. Okay, so let's bring this all back together. A random variable then is a variable that takes on certain potential number values with corresponding probability. So usually we name our random variables with an uppercase letter like uppercase X, uppercase Y, like we saw in this last example. And so for our particular case, Jessica can have anywhere between 1 and 4 encounters, and obviously things are going to vary here, but how much should they be varying? What should she expect, and what kind of standard deviation or deviation from that expectation will there be? Okay, and so when we're talking about discrete random variables, discrete meaning just we're doing counts, so 1, 2, 3, 4. So when we talk about what values X can take, we're talking about whole numbers. And so the expected value of the random variable is going to be the population average for that distribution. And the way this works is it's going to have to be a weighted average rather than fair sharing. Because remember, with just a data set, we would add all the numbers together and divide by how many numbers there were. So giving equal weight to each of those values in our data set. Here, we're going to have the weights distributed based on their probability or likelihood of coming up. And so that's where we're going to do a little bit different calculation to find that expected value or mean for the random variable. So the expected value of a random variable is given by, first of all, we want to use the symbols correctly. So that's a E of X is what we use for that symbol. And that is going to be equal to the sum of each of the data values times its probability of occurring. So one way you can think of it is we could take each individual one and we're going to multiply that by the probability of it plus the next data value times the probability that it's going to occur plus and so on. And how we usually shorthand that calculation is to say that it is the sum. That's what that symbol represents, is sum of each X times the probability that X is equal to that value. Okay, and so that's how you'll usually see that formula displayed, is with the summation notation. All right, so based off of Jessica's Pokemon encounter scenario, calculate the number of encounters Jessica should expect while looking for a rare creature. So we're looking for the expected value of the random variable X, which was the number of number of encounters Jessica has. And we're going to take each of our values that variable can take times their probability of occurring. All right, so I'm looking basically back over at my probability distribution. These are the values X can take, and then these were the probabilities. So when we're doing the calculation, we're going to do a multiplication, I'll finish this, we're going to do a product across each row in this case, right? We're going to do these products and then we're going to add them together. All right, so that's what we're wanting to set up in our formula over here. So we're going to take each of our possible outcomes, so starting from 1, and then we're going to take the product of that with its probability of occurring. And since there was a 10% chance of having one encounter, times 0.1, plus the value of the next outcome, which was 2 encounters, and the probability of that was 0.09, plus the next number of encounters we could have times the probability of that number of encounters, plus 4 times the probability of that number of encounters. And then that should come out to 3.4, and units on this would be encounters. Now, notice here we're going to go to 1 decimal place, and that is based off of our usual rule of thumb that will take our means and standard deviations to 1 decimal place more than what our data values were given. And so our data values in this case are our possible outcomes, which were 1, 2, 3, 4, and therefore we'll go to 1 decimal place on this. Okay. Now, the other thing I just want to make sure, in case anybody is uncomfortable with, it's like 3.4 isn't a possibility, right? But it kind of is. These averages are never going to go back to the more real life possible values, right? We don't want to always round to a nearest whole number, or else we lose that accuracy for comparison, right? So if we were thinking about the number of, or the average number of children that industrialized countries have, pretty much every industrialized country would average, if we rounded to a whole number, to 2 babies, or 1 or 2, or I guess a lot of the times 1 now, but 2 or 3 babies, right? And so that doesn't do us much good for comparison. We want to be able to get to at least that 1 decimal place to look at those smaller incremental differences between groups and sets. So do make sure you keep those decimals, even if it is not actually a valid outcome in the real world. All right, so let's try another example here. We are planning on flipping a coin twice. We're going to let X represent the number of heads. So that is our random variable. So X is our random variable. Random variable X equals number of heads. And in this case, it's in N equals 2 flips. Okay. So we're going to draw a tree to show the possible outcomes. That's going to be our first step. And this is often going to be our first step, to try and visualize what is happening in the real world. And so we have the option of getting heads or tails on our first flip, and then we're going to do a second flip, and that's going to be possible heads or tails as our second option for both of those. Okay, probability, we're going to assume a fair coin. We also do not have in coin flipping a total population that we're drawing out of, so we're going to rely again on that like a percent, so that there is a 50% chance of heads, 50% chance of tails. Okay, so 50-50, leave that as the decimal. And then we're going to think about what our possible outcomes were here. So this one, we're going to have the probability of heads and heads. That would be equal to the 0.5 times 0.5. This one is the probability of heads and then tails, also 0.5 times 0.5. And order matters, so we care also about the case where we have tails and then heads as a separate outcome from heads then tails. And then we have the probability of tails and tails, and that is also 0.5 times 0.5. Now what we care about though for our random variable is X being the number of heads that we're getting out of each of those flips. So we're going to go now and look at that. So X, in this case, we have 2 heads, so that's equal to 2. This case, we have X is equal to 1, X is equal to 1 being the number of heads. And then in this last case, when we have both tails, X is equal to 0. All right, so now we want to use that and we can come up with that probability distribution. So we know that we want to have X be the listing of the possible values, and then we want the probability of each of those outcomes. So X could be 0, 1, or 2 based on our analysis of the scenario, right? We saw that X was 2 when we had 2 heads. We could have 1 when we had heads and tail combinations, and then 0 when we got both tails. So the extremes are usually very easy to calculate. They're just going to be straight across that probability calculation of one branch. So the 0.5 times 0.5 for 0 heads, or getting 2 tails, right, is coming from this branching down here, and that is going to be equal to 0.25. Okay, straight from that. And then similarly, our extreme for having 2 heads, just that one branch is involved, and it's just going to be the product of 0.5 times itself twice, which is 0.25. Now the case for exactly 1 heads is coming from these 2 branches, right? So we're going to need to add those probabilities together. So we'll have the 0.25 from the first case plus the 0.25 from the second case, and that is going to come out to 0.5 for the probability, or 50% for the probability of getting exactly 1 head. Now, the other thing you want to recognize is, again, probability distribution. We are adding to 1. So if you know the extremes, like the 0 and 2 case, we could even just do a subtraction from 1 to find out what the probability of getting exactly 1 would be. Excuse me. Okay, so now that we have our probability distribution, we can go ahead and use that to calculate the expected value. So the expected number of heads we should get. All right. And just flipping twice, 50-50, you can probably go in your head and go, oh, well, it's got to be somewhere between 0 and 2. You should never get a number bigger than 2, right? And, well, it makes sense that we should get 1 out of 2, right? That's kind of the ratio for 50%. So let's go ahead and see if that pans out. So expected value of our random variable x is going to be each of the outcomes, and I'm looking at my table here. I'm going to take the 0 times the 0.25, so across the row, plus 1 times 0.5, plus 2 times 0.25. Now, in the cases where you have a 0, I know they go to 0. It's a nice, easy calculation, but please still show that in your calculation. And in terms of work being shown for this, I want to see all numbers that are going into the calculation, and then you can just go straight to the answer. And for this one, lo and behold, it is 1 head that we can expect to get. And so to explain what this means, this is based on long run relative frequency. It's not what we're going to get every individual time. We can't predict from this exactly what we're going to get in one case. But were we to do this process over and over again, we would find on average, we're going to get 1 head. Right? Sometimes we'll get 0, sometimes we'll get 2, more often we'll get 1, and then we'll average all of those outcomes together, and we should get around 1 head. So this is over the long run, we can expect to get 1 head when we flip 2 coins, or flip a coin 2 times. Let's go with the same wording. Flip a coin 2 times. Okay. So again, this is an over the long run average that we're calculating here. All right, so next example, Oregon Keno 3-spot game lists the probability of winning $2 at 1 in 8, the probability of winning $25 at 1 in 73. And so we want to let X represent the amount you will win in one play of the game and to calculate the expected value of that. So this doesn't need a tree in this case. We're given the probabilities. Trees are there to help us calculate probabilities. So if we're already given them, then we don't need to worry about it. So let's go ahead and run through our possible outcomes and then assign the probabilities in our table or probability distribution. So possible outcomes and the probability for each of those. Okay, so we could win $2. Great. And we actually know the probability is going to be 1 in 8. So 1 out of 8 as a fraction. That works. We can convert it to a decimal later. It's all good, or leave it as a fraction, doesn't much matter. Then we could win $25. Nice. 1 in 73 chance of that. Now, the one thing that's not listed here, but we also need to recognize is another outcome is when you don't win. If you lose, right, you're not going to get any money. And that still has probably a much higher likelihood of happening. And we don't know exactly the probability, but we can calculate it based on the fact that our distribution, our table here, should have probabilities adding to 1. So I can take 1 minus the probabilities I already know. So 1 minus 1/8, and then minus also 1/73. Now, usually when you do these calculations, we're going to have a least common denominator that's all big and nasty. So at this point, I would just switch over to decimals. Okay, and so that's going to be a 0.8613 to 4 decimal places. And that's the norm for our probability. How we want to express probabilities is in decimals to 4 decimal places, or as an exact fraction when it's reasonable to do so, so in a table situation. All right, now I want to calculate the expected value, and I use my table to do this. So my expected value of X will be equal to each of my outcomes times the likelihood of occurring. So plus 25 times 1/73 plus 0 times 0.8613. And again, I know that equals 0 and doesn't actually contribute to our calculation, but please show me that that is part of what you're seeing as the calculation that's occurring. All right, and so then this in your calculator, please get in the practice of trying to do this all in one calculation as well. That'll make sure there's less chance of having inaccuracies in your calculation and people are getting the same basic outcome. Now this is money, right? Because that's kind of what we're listing. And so we'll go to 2 decimal places on money values as a norm. So this is going to come out to 0.59 or 59 cents. So over the long run, we can expect to win on average 59 cents per play. Not too bad. So if it costs $1 though to play, should we be playing this game? Well, then we're running into a little bit of trouble. So we need to take our winnings that we're getting, so that 59 cents, and subtract the cost to play. And then that means that when we look at the net cost or our net winnings, we're going to be coming out negative 0.41 or 41 cents. So on average, you're actually going to be planning to lose 41 cents a game. So you can actually expect to lose 41 cents per game. So no, you don't want to play. So no. And this is how we'll usually make a decision on whether something is worth using for investment purposes or what have you. And most of these games are going to come out with a negative net winnings, and that means we don't want to play them for investment purposes. We keep playing it over and over again. We can expect on average to lose on each of them. The occasional time we might win, we might come out ahead, right? But those are when averaged all out over multiple game plays, we're going to come out in the red, right? We're not going to be ahead of the game. If we had an expected value that was positive, even 59 cents, well, then it's actually a worthwhile investment because you can play multiple games and come out ahead by at least that little bit for each game on average. Now, never going to encourage any sort of gambling, but if you can run through the odds and see that it's in your favor, maybe it's not such a bad idea. But I'll tell you now, none of the games that are actually played are. So it's very rare that you would have that situation come up. All right, so it's obviously possible for someone to win a fair amount of money when playing Keno, but it's not very likely. And so that's going to bring up an issue of spread. So how far should we expect our winnings to vary from the center? Okay, so remembering that when we're thinking about amount of spread, we're thinking of how far on average values are going to vary from the mean. And so that is a measure of standard deviation. And so that's what we're going to try and calculate for these. So the standard deviation describes the spread for a random variable. It's a weighted gap size from the center and depends on the likelihood of each of the events. And so we're going to calculate this in, unfortunately, a fairly long process. Don't worry, we won't have to do it for too long. But just like our standard deviation calculations with data sets, we're going to start with doing the calculation of the variance first. So calculate the variance and then take the square root of that to get to the standard deviation. And the variance, we're going to be using these symbols here, the variance, standard deviation, whenever we're talking about these distributions. But they do kind of pair with the symbolism that we know from populations because it's effectively the population of this distribution. And so we can kind of think of those synonymously, right? So this is your population parameter symbol. And so sometimes you'll see things listed that way in other resources. So don't get too confused by that. Just note that for our class, we're going to stick with the E of X notation rather than mu for the mean. We're going to use variance of X and standard deviation of X. So SD and VAR. All right, so the calculation, we're going to use that shorthanded summation type of form again for this, and that is the sum of. Okay, so we're going to take all of our values of X and then we're going to subtract from that the expected value of the whole distribution. Now, this is very similar to our regular calculation of standard deviation, right? It is how far on average data values are from the mean. So we need to look at that difference first. How far are these data values from the mean? All right, and so that's what that is. Now, it could be both positive or negative. So to kind of get rid of that possibility. We want only positive values. So we're going to square all of that. And then we're going to multiply that by the probability of the outcome. So when x is equal to that little value of x. All right, and so we're doing that for each of the data values in the list. Now, the other thing we want to notice here is that we've squared things. So the variance, just like with our regular data, is going to have squared units. So variance has squared units, and that's due to the squaring of that difference. Okay, and the other thing we're going to see is though that's going to go back into the regular units when we take the standard deviation, because we're going to take the square root of that, right? So the standard deviation is just the square root of the variance of x, and then we're back to units of our distribution. So standard deviation is back to the units of the distribution. All right, so we want to calculate the variance and standard deviation for the Keno example. All right, so if we can, I'm going to make this a little smaller so we can see the table. All right, so we're going to calculate the variance first. Always go through the variance for me. That way I can kind of see, because calculation errors can happen, and especially with this situation, we want to make sure that I get to see what your intention was with the variance and then the square root, because otherwise if you just do it all in one and I don't see any of that process being laid out, then I'm not too sure what happened to get the numbers that you did. All right, so the variance is going to take each individual value x. So I'm going to start with 2, and we're going to subtract from that the expected value. E of x was 0.59. Okay, and that was positive, so we keep that negative. If we had an expected value that was negative, then that would change the sign in this portion of the calculation, right? And that's going to be squared times the probability of that outcome, which was 1/8. Then we're going to go to the next value. So plus 25 minus the expected value, 0.59 squared, times the probability of occurring. Plus, now in this case, we do need to keep our zeros, right? This isn't going to disappear because we're doing 0 minus 0.59 squared times its probability of occurring, 0.8613, right? 86% chance of actually losing, not winning anything. All right, so for the variance, I can come back to, our regular size. That is going to then be equal to 8.7111. I'm going to leave a bunch of extra decimal places. I want to have at least one more decimal place than what, I think it's just the first two. I want to have at least one more decimal place than what I'm going to round to in my final step of calculating the standard deviation. So I could have left it at 8.71 and then rounded to one decimal place. But I gotta remember, I've got some money, right? This is money. So I'm going to want to end with 2 decimal places. So that's why I'm going to 3. And the other thing we want to remember is the units on this. So the units are squared. This was a money situation. So normally I would have dollars, but since I'm squaring that, it is dollars squared. Now, please don't re-square the number part. The number part has already been addressed as part of the formula. It is just the units that we're wanting to show we're also getting squared. And then the standard deviation of x is going to be the square root of that. 711, getting a little overeager with those ones. And then that comes to $2.95. All right, so we can expect to win that 59 cents, give or take $2.95. Now it becomes less of a sure thing, right? So when we're looking at the possibilities kind of ranging into the negative zone, then it becomes less of an investment worthy proposition, right? Okay, so that's the idea with the standard deviation, is to give that wiggle room, just like we were doing in the regular calculations of standard deviation with sample data. All right, so let's take a look again at Jessica. She's playing Pokemon Sun. We have already created the probability distribution for the number of encounters that she has. So remember, we had X is equal to 1. That probability was 0.1. Having 2 encounters, 0.09. Having 3 encounters, 0.081. And having 4 encounters, 0.7290. And we had already calculated the expected value, and that was 3.4 encounters. Okay, so now we want to use this to find the standard deviation. So we have the variance first. So the variance of X, I'm going to take each outcome and I'm going to subtract from that the standard deviation, or the expected value squared times the probability of occurring, plus the outcome minus the standard, or the expected value squared times the probability, 0.9. There we go. Plus, and then we're going to have the next outcome minus the expected value squared times the probability of occurring, and then plus our last outcome minus the expected value squared times the probability of occurring, 7290. There it is. All right, and this is a big, complicated calculation, so you want to go very slowly in your calculator, check after each part of that calculation that you've got things entered correctly, and you should get 1.0278. Again, I'm just leaving a bunch of decimal places here because this isn't my final answer, and I don't want to lose any of my accuracy. So this will be encounters squared, since we are in variance and all of my units get squared for variance. And then I'm going to use that to get to the standard deviation, which is the square root of 1.0278. And that comes to 1.0 to the 1 decimal place encounters. Okay, so she can expect to have 3.4 encounters to get to a rare one, give or take 1 encounter. So she can expect to have 3.4 encounters to get a rare one, give or take, or take 1.0 encounters. So again, our interpretation of the expected value and standard deviation together take that similar form to what we were looking at with the sample data. So we are having this expectation of this amount, give or take some of that wiggle room that we're calculating with the standard deviation. That is a U. Let's make sure that's a little clearer. There, counters. All right. And would it be unusual for Jessica to find the rare creature in her first encounter? What is the Z-score for this event? All right, so remember, if we are trying to find unusual, that means we're looking for Z-scores. Tells us how many standard deviations the data value is from the mean in our distribution. And a random variable is a distribution, right? It's showing our possible outcomes. We could draw that in the form of a histogram if we had wanted to. All those good things. And so what we want to recognize is that when we have our expected value of X, this is our mean. And we just calculated our standard deviation of X. There's our standard deviation, right? And those are the numbers that we need to calculate our Z-score. Z-score is just equal to our data value minus the mean divided by the standard deviation, regardless of the type of distribution. Remember, it could be sample, could be population, and now we're looking at it in terms of our random variable distribution. So X, or Z, is going to be equal to our data value. So in this case, it is just having 1 encounter. So if she came across that rare creature in her first encounter, that means that's the final number of encounters she's going to have. So our data value is 1 minus our mean was 3.4. That's what our expected value was, and divided by our standard deviation, which we just calculated to be 1. And then if we run through that calculation, we're going to have negative 2.40. Remembering again, z-scores are signed and can be positive or negative. Negative z-score means that our data value was less than the mean. And the fact that it's negative 2.40, that is more than 2 standard deviations from the mean. So yes, it would be unusual. So yes, it would be unusual since it is more than 2 standard deviations from the mean or expected value of x. All right, so that kind of goes through the process of the calculation. You'll want to do some of that practice yourself and definitely go back into these examples, do the calculation on your calculator to make sure you're coming up with the same numbers as me. That's usually the biggest issue with this stuff, is making sure that you're getting your calculator to work in a predictable way. All right, and let me know if you have any questions, and we'll see you next time.